Okay, so last time we got into chapter-ish something. All right, so we got into chapter 17, I think. So 17 is all about really electrochemistry. And really, it's all about sort of redox reactions. So last time we went over the idea of what that is. So remember that when something goes through oxidation, there's several definitions, but the one that we use the most is that it typically will lose electrons. Once again, some other definitions of oxidation is the gaining of oxygen as you go from reactants to products. Also, the loss of hydrogen as you go from reactants to products. So those are a few different definitions of oxidation, but pretty much in general chemistry, that is really the one that we focus in on. Reduction is pretty much the opposite in all those sort of definitions. So reduction is when something gains electrons. Also, it means that it will lose oxygen from reactants to products, and it will gain hydrogen as you go from reactants to products. Once again, the gaining of electrons is typically what we look at here. These two definitions a lot of times are sort of used in more organic chemistry where you're doing with a lot of nonmetals and nonmetals sort of happening. One way that we could basically follow what is going on is by obviously identifying the oxidation number or state. And remember, some of the general rules of oxidation number or state is anything that is uncombined in their natural form pretty much will have oxidation number of 0. If you have oxygen, that's usually a pretty good place to start. It will have an oxidation number -2, again, unless it's peroxide. Hydrogen is typically +1, again, unless it comes after a metal, will be -1. Any type of ion that has a charge will be the same as its oxidation number. So the charge is the same as its oxidation number. And remember, when you add up all your oxidation numbers, they need to equal the charge, if there is one, on the ion. If it's not an ion and doesn't have a charge, then you need to add it all up to 0. Remember that when things take on sort of oxidation numbers or states, they are different than the normal sort of, again, ionic charge that we sort of associate with things. If you are dealing with an ionic compound, then everybody will have their normal sort of charges. But in a covalent bonding situation where they are sharing electrons, again, even things that we normally associate as having a negative sort of charge, if you will take on a positive, in some cases, oxidation state. So again, chlorine is an example we saw, again, can have like a +2, a +3, maybe a +5 sort of happening depending on what is going on there. In addition, if you want to sort of easily determine what is being oxidized, what is being reduced, you could just use a basic number line, positive numbers to the right, negative numbers to the left. When things get oxidized or go through oxidation, they become more positive. So if you follow the oxidation states from the reactants to the products, and it's kind of moving in that direction along the number line, then that thing is going through oxidation. When things gain electrons, they get reduced, they become more negative. So if you follow the oxidation number and it started moving to the left there and becoming more negative, that guy will be going through reduction. There's also the oxidizing agent. And remember that the oxidizing agent is actually the substance that gets reduced, while the reducing agent is the substance that gets oxidized. And again, they're called that because they basically cause that effect in the other substance or species that is present. The things that are being oxidized, the things that are being reduced, the oxidizing agent and the reducing agent are always found on the reactant side of the equation. We also can take a half reaction for each of these things. And when we write half reactions, and we have electrons that end up on the product side, this is usually an oxidation half reaction. When we have electrons that are on the reactant side, like they're being gained, that would indicate a reduction half reaction. So when we have just basic sort of redox reactions, and you need to add both of these half reactions together, which is why they're called half reactions, because when you put them together, you get the overall reaction that is happening. Remember that the electrons always need to be the same number in both half reactions. And again, as we talked about, sometimes you may have to multiply a half reaction by a number, or you may have to multiply both half reactions by numbers to get them to the same. But you always want to make sure the electrons are always on opposite sides of the arrow, and then also they are the same before you add them together. And you want to do that in a basic redox sort of problem. When you are balancing redox reactions in acidic or basic conditions, it is a little bit more complicated. There's some steps that we follow. We basically will split off into the half reactions. We then want to balance all elements except for hydrogen and oxygen. Once you balance those guys like normal by putting coefficients in front of everybody, you then balance the oxygen by adding water to whatever side needs the oxygen. And remember that when we do add water, every time we add a water, we are also putting in there 2 hydrogens. So to make sure everything stays balanced, to the opposite side of where you added the water, you need to add 2 H pluses for every water that you added. And again, that's going to keep basically the hydrogen still balanced when you do that. At that point, you can then add electrons to balance each half reaction charge on each side. So remember that you're going to be adding the electrons, and they are negatively charged. So you're going to add it to whichever side needs the negative charge. The goal here is not necessarily to get both sides to 0 in terms of overall charge, but they do need to be the exact same number on both sides. So whatever that number may be, plus charge, minus charge, 0, they need to be the same on each side. Once you do that, you can add the half reactions back together. Once again, you need to make sure same number of electrons in each half reaction. And again, if you do not have the same number of electrons, you need to multiply them by a common number to do that. The electrons should always completely cancel out, because the idea of a redox reaction is this: if somebody is being oxidized, somebody is definitely being reduced at the same time. They always happen together, and however many electrons the guy being oxidized loses is how many electrons the guy that's being reduced will gain. Once you do that, you are pretty much going to be balanced in acidic conditions. By the way, obviously, in addition to the electrons, if there's anything on opposite sides of the arrow, that's the same thing. You could either reduce it down or completely cancel it out if it does do that. Once you have it balanced in acidic conditions, and by the way, once you know that, because there should be an H plus in there when you balance it. If you wanted to go to basic at that point, you would add OH minus to both sides. Equal to the number of H pluses you have. And this is the point where you have OH minus and H plus on one side of the arrow, These guys will combine to make water, and then you can reduce down waters. Usually you'll have some excess waters on the other side. You can kind of reduce it down, and then you would be balanced in basic conditions at that point, and you would see OH minus in the final reaction to tell you that you are balanced in basic conditions. Other things that are sort of can happen along the way here is if you start with a half reaction where maybe you have something like this, and you're starting with an extra H to begin with, you should add right off the bat just an H plus to the other side to balance it out. Otherwise, eventually you will be short hydrogens if you don't do that. So sometimes you will get a half reaction where you kind of have an extra H and just add an H plus to the other side and continue like normal, and that will take care of that. Other things that we talked about that's important as well is it's a really good idea before you start it, the whole balancing aspect of it, that you really do sort of figure out which one's your oxidation and reduction half reactions. That way, when you add your electrons, you can double check that you hopefully did it to the correct side. Again, the oxidation electron should be added to the product side. The reduction electrons should be added to the reactant side. Any questions on that fun stuff? Yes. All right. So why don't we try another one here? Why don't you do this guy here? So starting with this equation, we want to balance this guy. We'll do, what does it say there? Basic, I think. Yeah, so let's do it in basic conditions. So take a few moments or more to balance this up. Remember that when you balance these equations and it's all said and done, it needs to be balanced basically two ways, like a normal equation, the same number of elements on both sides, and it also needs to have the same overall charge. Okay, let's take a look, see how you're progressing. So again, a good idea up front is to maybe assign some oxidation numbers and stuff to everybody so you have an idea what is going on. So our I minus here would have an oxidation state of -1. The oxygen here would be -2. There are 4 of them, which gives us like a -8. Needs to equal -1, which means the Mn here has an oxidation state of +7 in this case there. Coming here to the I2, that is iodine in its natural state uncombined, so that is going to be an oxidation number of 0. And once again here, the oxygen would be -2, that's a -4, needs to equal 0. So that is a +4 happening there. First off, any questions on assigning the oxidation numbers here? What's that? So any ion by itself that's monoatomic, whatever the charge is, will be the oxidation state of it. Yeah. The I2 on the other side is how it comes naturally, so it's uncombined, so we'll have an oxidation state of 0. Other questions? So we could really use this, and again, if you want, you can do a little number line action here and see what's going on. We can see that the I minus is starting at -1 and ending at 0, which means it is going towards the positive side. That means that really this guy is going through oxidation. We could do the same thing for the Mn. The Mn is starting at +7, which is like here, and it's ending at +4, which means it's actually moving in the negative direction, which because it's becoming more negative, it is going through reduction. That also means that the I minus here is my oxidizing agent or reducing agent. This would be my reducing agent, right? Because it is getting oxidized. The Mn here actually is our oxidizing agent. There. All right, so now that we have that all sort of squared away, that's good information to know as we go through this to make sure, you know, we sort of put things in the right spot here. We're going to first split this up into its 2 half reactions, and it is as simple as there's an iodine there, and on the other side, it goes with an iodine, basically. And the second guy is, I see an Mn on the left, and it goes with the Mn there on the right, basically. We've already identified here that our I is our oxidation half reaction. This would be our reduction half reaction. Now, the first thing we do after we split it off is we want to balance all the elements just like a normal equation, except for oxygen and hydrogen. And in this case, we do need to put a 2 in front of the I minus. In terms of the Mn, we have 1 here and 1 here, so we're good. We don't have to do anything with that at this point. Now, once we've taken care of all the other elements, it is time to balance the oxygen. And once again, we're going to balance oxygen by adding water. In the first half reaction there's no oxygen on either side, so we don't have to worry about it. On the second half reaction, on the left-hand side, there's 4 oxygens. On the right-hand side, there's only 2. So it is the right-hand side here that needs 2 waters. And again, those 2 waters are going to provide the 2 oxygen that is needed. But once again, as we talked about, for every water that we add, we are also adding the hydrogen. So we need to go back to the other side. And in this case, add 4 H pluses. Once again, if you do not do that, you will be off on hydrogen and charges and stuff like that. Any questions up to there? At this point, we have now balanced oxygens and hydrogens. What is now left to do at this point is basically add our electrons. And we want to add our electrons to really balance out the overall charge on each side. So if we look at the first half reaction here, overall charge is -2 from that guy. Overall charge is 0. So here it is the right-hand side that needs a couple of electrons, which will provide a -2 on the right to match the -2 that is on the left. We're going to do really the same thing here on the bottom. This guy here is going to contribute +4. This entire thing contributes that -1. That means overall here on the left-hand side, we basically got +3 happening. On the right-hand side, this guy is 0 and this guy is 0. That means the left-hand side here needs the electrons, and to get it to 0 in this case, we do need to add 3 electrons. That gives us -3 over here and gives us 0 happening on both sides. Any questions on that? Here is where we can, make sure we did everything correctly. As we talked about before, you should never, ever add electrons to the same side. Here we added electrons to the right-hand side, which does match that this is the oxidation half reaction. And on the second one, we added electrons to the left-hand side, which matches the fact that this is a reduction half reaction. Any questions up to there? We're now at the part where we will be adding these 2 half reactions together, but remember that we cannot add them together until the electrons are the same in each half reaction. And in this case, they are not. We got 2 in the first one and 3 in the second one. That means in this case, we need to actually multiply both half reactions by a number. 3 and 2 is 6. Yeah, so we need to really multiply the top half reaction by 3. And we're going to multiply everybody in the second half reaction by 2. I'm just going to write some of these extra numbers here. Just give a little bit more room. Okay, so I'm just going to bring both reactions underneath it there. So, and multiplying my numbers across. So multiplying the top one there, that's going to give me 6I minus goes to 3I2 plus 6 electrons. Multiplying my 2 to the bottom one is going to give me 6 electrons plus 8 H pluses plus 2 of the MnO4 minus gives me 2 of the MnO2 and 4 waters in this case. Now that I have the electrons the same on both half reactions, we're ready to add these together. Once again, anything on opposite sides of the arrow can cancel or reduce down. Anything that's on the left-hand side stays on the left, and anything on the right-hand side will stay on the right-hand side. Once again, electrons should always completely cancel, which they do. And I believe that is all that's going to cancel here. So we're going to do 8 H pluses plus 2 MnO4 minus plus 6 I minus. That's everything on the left-hand side of the arrow. On the right-hand side of the arrow, we have 3I2 plus 2 MnO2 plus 4 waters. Any questions so far? If I was balancing this reaction in acidic conditions, I would be done. Yes. So we could check just to make sure we did it right for acidic. We have 8 hydrogens on the left, 8 on the right, 2 Mns on the left, 2 on the right. We have 6 iodines on the left, 6 on the right. We have 8 oxygens on the left, 4 oxygens on the right, plus another 4 is 8. Overall charge here on the left-hand side is +8 from the first guy. -2 and -6 is 0. Overall charge on the right is 0. So again, this would be balanced both ways that it needs to be by charge and elements if we were done with acidic conditions. And once again, we know we are in acidic conditions because I see this guy right here. H plus tells me it's an acidic sort of equation that's been balanced. First off, any questions on that part? Now, as we talked about last time, probably the easiest way to balance something in basic conditions is to pretty much do what we just did. And here at the end, you can turn it into basic conditions by adding OH minus to both sides. So here we're going to add OH minus to both sides, and it's going to be equal to the amount of H plus that we have. So since we have 8 H pluses, left-hand side gets 8 OH minuses, right-hand side gets 8 OH minuses. The side where we have OH minus and H plus, once again, will come together to make water, and that will give you 8 waters. On the left-hand side, again, on the right-hand side here, I do have 4 waters, so you can subtract 4 from the right to the left, and you will end up with 4 waters on the left plus 2 MnO4 minus plus 6 I minus goes to 3I2 plus 2 MnO2 plus 8 OH minus. And if I didn't screw anything up here, this would be the properly balanced equation in basic conditions. It should still be balanced both ways. So once again, if we take a quick look, 4 times 2 is 8 for the hydrogens on the left, 8 for the hydrogens on the right. We have 2 Mns on the left, 2 on the right, 6 iodines on the left, 6 on the right. Oxygen, we got like 4 here and 8 more there. That's 12. Here we have 4 oxygens and 8 more is 12. Overall charge, this guy is 0. This guy contributes -2. This guy contributes -6. That's a -8 overall charge on the left-hand side. This guy contributes 0. This guy contributes 0. This guy contributes -8. So we are equal in terms of the charge on both sides, and we are equal in terms of the elements on both sides. And much like the acidic one, I know this is a basic equation because I see OH minus there in the final product there. Any questions on any of those steps? Yeah. You definitely need to know how to do these for sure. Yes. All right. All right, let's do one more just to make sure. So in the next 2 labs, you don't cry when you have to do all these. All right. Well, actually, let's see this one here. We'll skip that one. Let's go with this one. Let's do it in acidic conditions. A little dichromate, a little oxalate, a little CO2 action. Yeah. Okay, let's take a look and see here. So once again, I'm going to start with oxidation numbers. So we got a little dichromate. So the oxygen here is a good place to start, which is -2. That gives you like a -14, and our overall guy is -2. There are 2 chromiums here, which means each one in this case is a +6, which would give us a +12 and a -2 overall. Coming here to our oxalate, our oxygen is -2. There are 4 of them, will give us -8 equals -2. Once again, here there are 2 carbons. So in this case, we need to get to 6. So each one would be +3 in this case in terms of its oxidation state. This is a ion by itself, which means the charge is the oxidation number here, which would be +3. And with CO2, our oxygen would be -2, gives us -4. Does equal 0 in this case, which means the carbon here would be +4. Any questions on how to assign those oxidation numbers? Once again, if you want to do the number line approach here to have to maybe not think about it too much, we'll start with chromium, which is +6, which is here, and it ends at +3, which means it is moving in a negative direction, which means this guy is our reduction guy that's being reduced. By default, this would mean that this is the oxidation, or the thing being oxidized. We can see it by looking at the carbon. Carbon starts at +3, ends at +4, which means it's moving in the positive direction and is being oxidized. So that would mean that this guy here, our dichromate, would be our oxidizing agent, and the oxalate here would be our reducing agent in this case. Any questions on how to figure all that out there? All right, so now we're ready to get into our balancing here. So we're going to split it off. So I'm going to keep chromium with chromium here. So Cr2O72 minus and our Cr3 plus. And I'm going to keep carbon with carbon in this case. So that's a C2O42 minus and a CO2. Once again, we've identified this first one as our reduction half reaction, this one being our oxidation half reaction. Now we will proceed to balance all the elements other than oxygen and hydrogen like normal. In this case, we do need to put a 2 in front of the chromium, and we also need to put a 2 in front of the carbon as well to take care of 2 carbons on both sides. We're now ready to move to oxygen. So the top half reaction has 7 oxygens on the left, which means we need 7 waters there on the right-hand side. Because we put 7 waters on the right-hand side, we then also will need 14 H pluses happening there on the left-hand side. On the bottom half reaction, we got 4 oxygens on the left, and by putting the 2 in front of the CO2, we end up with 4 oxygens on the right, which means we are good on that one. We don't need to add any waters to that particular one. Any questions on that so far? So now that we're good on everything, oxygens, hydrogens, we're ready to balance overall charge here by adding our electrons. Once again, this guy contributes a +14. This guy contributes the -2. Which means overall on the left-hand side there, we got a +12 happening. Right-hand side, 2 times +3 is +6. And this guy contributes 0. That means in this particular case, the electrons need to go on the left-hand side. And we would need 6 electrons in this case. That would then get us down to +6 on both sides. Yeah. Any questions on that there? Coming to the bottom, this guy's going to contribute basically that, which is -2, and this guy's contributing nothing, which means the right-hand side here will need a couple of electrons, which will now give us -2 and -2. Then obviously here with our 6 electrons gives us a +6 and a +6. Any questions on that there? That looks like in this case, we actually just need to multiply the bottom half reaction to get it to 6 electrons because we're ready to add these together. So this bottom half reaction, we will multiply by 3 to get us to 6 electrons. Once again, I'm just going to rewrite it underneath here. So copying everything down, including the top reaction, which I didn't multiply by anything. So that is 6 electrons plus 14 H pluses plus Cr2O72 minus. A couple of these guys here and 7 of those. Well, multiplying that 3 on the bottom there gives us 3 C2O42 minus. Goes to 6 CO2 and 6 electrons. At this point, we could add these together where the electrons should cancel. And I believe that is it in terms of canceling. Everybody on the left-hand side of the arrow will stay there, and everybody on the right-hand side will stay there. So that's 14 H pluses plus our dichromate plus our oxalate here. Going to give us that there, a couple or 7 waters and 6 CO2 in this case. So once again, here we should be balanced both ways. So we got 14 hydrogens on the left, 14 on the right, 2 CRs on the left, 2 on the right. We got 6 carbons on both sides. Oxygen, there are 7 in this guy and 12 in that guy. That's a lot. That's like 19, I think. And we got 7 there and 12 there, which would be 19 as well. Overall charge, this guy contributes plus 14. This guy contributes minus 2. This guy 3 times minus 2 is minus 6. So that is a net of a plus 6 on the left. Over here we have plus 6. This guy contributes 0. This guy contributes 0. So plus 6 on both sides. We are golden, as we like to say there. Any questions on that there? Once again, we do see we end up with H plus here, which tells us obviously we did something right in an acidic sort of condition. So any questions on how these steps to balance these things? Yes. Just gotta keep track of everything. If you rewrite it, don't screw up rewriting it. That's a very common mistake. All right, so that was hopefully reviewish. If not reviewish, hopefully new material for you. But you do need to definitely know how to do this for what's coming up, obviously. So we'll get now into really the heart of the chapter here, which is galvanic cells and electrochemistry. So this is a galvanic cell, and there's a couple of parts to a galvanic cell, which is really important. This is a galvanic cell that you can build in the laboratory. We used to build it sort of like this, but not anymore. But really galvanic cells are really redox reactions. So really what's going on in a galvanic cell is actual redox reaction. So there is something that is getting oxidized and there is something that is getting reduced in this reaction. So the basic parts to a galvanic cell is you can make it out of beakers there. And we have beakers that are filled with solutions, and in the solutions are ions. They are ions that are representative of our solid electrodes that we have here. In this case, we have a zinc electrode on the left, and we have zinc ions floating around in the solution there on the left because that's the zinc one. Here we have the copper one on the right, and we got some copper ions floating around in that solution on the right as well. They are usually connected via a wire, and maybe you have a voltage meter there where you could test the voltage. And they're also connected by what is referred to as a salt bridge. So a salt bridge basically connects both sides of a galvanic cell, and it's usually filled with some type of electrolyte solution like potassium chloride, sodium chloride, something like that. You put the plugs in there so it doesn't fall out, basically. On the left-hand side in this picture, this is what is referred to as the anode. And the anode is where oxidation occurs. So oxidation always occurs at the anode side in a galvanic cell. So basically what happens is these solid zinc guys, as you can see here from the half reaction, will lose electrons. And frankly, when they lose electrons, they get a charge, and things with charge pretty much are swimming around in the solution. So what happens is those guys will lose electrons. The solid zinc will then jump from the solid into basically the aqueous solution that is there and join the other zinc guys that are in that side. The result of that is the electron will then travel across the wire to the other side of the galvanic cell, which is known as the cathode side. And that is where reduction takes place. So these incoming electrons from the oxidation will come through. They will then join up with the floating ions that are in the solution, and they will reduce those guys that have charges, like in this case, from +2 to 0. And you can kind of think of it as they will then kind of jump out of solution and become a solid in this case. So anode oxidation, cathode where reduction takes place. The electrons, as they go across, will create a voltage, and the electrons could go out and really do some type of work. It's very similar to what pretty much like a battery does, right? When you put a battery in, shoot some electrons around, your whatever turns on and works and all those good stuff. If you look in the battery compartment, right, there's usually wire, right, where you kind of put the batteries in, and that's the same idea as the wire you see here. When we do this, the salt bridge plays a really important role. The cathode, you can think of it, there's sort of a charge difference, if you will, between sort of the anode side and the cathode side being a little bit more positive. And what that does is it helps draw the negatively charged electrons over to the cathode side and keep the whole thing flowing. The salt bridge plays a really important role because, as you can see in this particular example, our chloride ions are going this way. Our positively charged potassium guys are going that way. So you may be asking, well, why is like the negative guy going over there to the anode side, and why is the positive guy going to basically the cathode side? Let's say we ran this cell without the salt bridge. We were out of stuff at that point, but we were still able to have our electrodes and all this good stuff happening. What is essentially happening, if this is our anode side, right, and this is our cathode side, and we ran this, for example, without the salt bridge, as the oxidation occurs, we are then going to build up a lot of positively charged ions over here, right? And as those electrons go to the other side, the spectator ion that was in that solution is going to be pretty much the only guy left on that side, because all the positive guys are going to jump out of solution, and you will build up a negative charge on this side if you didn't have the salt bridge. Why would building up a negative charge on the cathode side and a positive charge on the anode side be a bad thing if you want electrons to go to the cathode? Exactly. Electrons are negatively charged, right? Which means you're really discouraging them from going that way because they're the same charge, right? And as you said, they would actually be more attracted to head this way. So your cell would pretty much stop working at that point. So the purpose of the salt bridge here is to dump negative charges into here to counteract the buildup of positive charges, while the salt bridge will dump positive charges over here to counteract the buildup of negative charges, and that allows the cells and the electrons to continue basically to go from one side to the next. Any questions on that there? No, the salt bridge is actually it's an aqueous solution, so it's basically just like a salt solution in most cases. So what we'll use, for example, I think when we do the experiment, I don't think we do it next week. This experiment, we do just regular redox experiments, but the one with the electrochemistry experiment, we used to do something like sodium nitrate, which is just a salt solution basically. It does a little bit, and that's how it's able to get there. The purpose of the cathode is to make sure it just all doesn't drop out. Frankly, is what the cathode is for. You can't plug this up really, right? Otherwise, nothing's going to go out of the salt bridge, right? But the cathode does allow, as you said, a nice slow sort of diffusion of that guy, into the other side there. Obviously, you plugged it up, nothing's going to get out. So again, it'll be like not having the salt bridge there or anything like that. Yeah. Other questions? Okay, so that's really the purpose of our salt bridge. Once again, if we look at what's really going on here, if we add these two half reactions together, we basically just need to have the same number of electrons, which we do. So in this reaction here, basically what's happening is we have our zinc, which is solid and no oxidation state. And we have our copper 2, which has a +2 oxidation state, and oxidizing our zinc to +2 and reducing our copper to no charge. So that's the overall, which is in this box here, reaction that is taking place. So you do need to know what a galvanic cell looks like. Yes, the different parts of it, where they're found, and all those kind of things. Now, a lot of times we do use electrodes that obviously are the solid versions of what's floating around in the solution. Sometimes, as we will talk about here and see in a second, sometimes the electrode itself is sort of an inert sort of metal because it's a gas, might be the anode or cathode. So there's no kind of solid representation of that. So sometimes they'll use something like graphite or platinum or something like that as sort of the solid electrode in those processes. So a galvanic cell, as I mentioned, there is sort of that difference in sort of the potential, and that's sometimes referred to as the cell potential, sometimes referred to as electromotive force, EMF, or the cell voltage. Pretty much in a question, if they ask you to solve for any of those three things, they're basically asking you to solve for the voltage of the cell is basically what they're asking you to solve for. 1 volt is equal to 1 joule over a coulomb. Coulomb is a unit of electrical charge, and a joule obviously is an energy. Here's a traditional galvanic cell you can build in the laboratory. Again, we used to do something like this. You could barely see it, but there's the salt bridge right there between the two. And again, you can see the solid electrodes. And you have a voltage meter there that will give you your voltage. And again, a positive voltage is usually a spontaneous sort of a process. Negative voltage, not so good. Cell doesn't work. Kind of equivalent to putting your batteries in backwards, right? Things don't work until you flip it the right way. And that's the nice thing about galvanic cells is just that if you get negative voltage, pretty much all you have to do is switch your anode and cathode, and then you'll have a positive voltage. So they work that pretty easily. Another way that sometimes reactions in galvanic cells are represented is by what is referred to as a cell diagram. So this is the overall reaction, redox reaction for what we were just looking at. And the cell diagram is what's on the bottom here. And this is the cell diagram. And it is always anode to cathode is how the cell diagram is sort of written. So this is the anode compartment. The two sort of lines represents the salt bridge. And pretty much if you needed to go from the cell diagram to the reaction, they're pretty much always sort of set up this way. First guy is a reactant, second guy is a product. First guy is the reactant, second guy is the product. So you can see reactant, product, reactant, product, basically. So that's what each of those single lines kind of represent the reactant to the product side of what's going on in the anode reaction. And obviously the reactant to product, what's going on in the cathode reaction. So that's how you can kind of turn a cell diagram into an equation. I just kind of do that reactant product is basically how it works. Other things that sometimes do show up in these cell diagrams here is, as you can see there, they will sometimes put the molarity down for obviously things that are floating around in the solution. As I mentioned before as well, sometimes you may have something like platinum or some other type of metal show up when you have something that's a gas. And in addition, if it's a gas, sometimes they will also include the pressure of the gas, which under normal conditions, and as we talked about thermodynamics, under standard conditions, right, that is a gas that has a pressure of 1 atmosphere. That is a solution that has a molarity of 1 molar. Again, so this would be sort of a standard condition sort of galvanic cell that's set up because the concentrations everybody is 1 molar. As we'll see later on in this chapter, when it's non-standard conditions, there's some other calculations you have to do, very similar to what we saw sort of with thermodynamics. Now, one of the most important things in sort of a galvanic cell and helping us understand what is going on in a galvanic cell is what is sometimes referred to as a potential. That is sometimes abbreviated as the SRP for standard reduction potential. It is basically a reduction reaction of what's going on, and there is a voltage that is basically accompanying that. Here we actually have a zinc electrode as our anode. In this case, we actually have a hydrogen electrode as our cathode. So in this particular case, as I was talking about earlier, because the cathode here is hydrogen gas, there's no really solid version of hydrogen that we can use as an electrode. So they're using a platinum electrode as sort of the solid version to sort of complete everything and have somewhere for the electrons to kind of go down and through here. In this case, what we see is the zinc is being oxidized as it goes from 0 to +2, and our hydrogen going from +1 to 0 is being reduced in this case to hydrogen gas. This is our cell diagram. So again, we have our concentrations, and again, the added platinum here just to represent that it is being used as the solid electrode. Once again, if we look at the overall reaction, we can kind of see it the same way. This is our reactant, that's our product. So reactant and product. And this would be our reactant, and this would be our product here. So reactant and product here. Once again, the platinum would not be in the overall reaction, but it does find itself in the cell diagram to represent that's what's being used as the physical electrode, but does not take place there in the reaction. Any questions on that there? So this hydrogen electrode is actually a really important one, and it is what is used here in chemistry basically to figure out all of the standard reduction potentials for everybody else. So much like in chemistry when they chose the carbon-12 isotope to figure out atomic mass for everybody else, they chose the hydrogen electrode as the standard to compare everybody else to, and they basically assigned it a voltage of 0 volts. So they assigned the standard hydrogen electrode, which is what this is sometimes referred to, the standard hydrogen electrode, sometimes referred to as the SHE, which stands for standard hydrogen electrode. And they arbitrarily sort of divided. The He is just the hydrogen electrode. It's not very standard, but the standard hydrogen electrode is the She there. And they assigned it an arbitrary value there of 0 volts. And this is a typical SRP reaction. When we look at the SRP reaction, they are always going to be reduction reactions. And as we will talk about in just a second, that's a little bit of problem. Some things we need to do, because whenever we have a reduction, we will have a oxidation that's going to occur. So when we look at these SRP values in these tables, one of the reactions are technically wrong. It's written the wrong way because they're all written as reduction reactions. So basically what they did is they kind of hooked up the standard hydrogen electrode to all kinds of things. And they were able to basically figure out the SRP values for other elements. So in this particular case, here's our zinc. This is our anode. This is our standard hydrogen electrode, which is our cathode. And they hooked it up and got a cell voltage of 0.76 volts when they did it. In this particular case, they were able to figure out using this equation here, which is an important equation. This is E of the cell, which is the cell voltage basically, is E of the cathode minus E of the anode. So what's important in this equation is what might not make sense right at this moment, but will hopefully eventually make sense, is this negative part. So this negative part is there because the anode is basically an oxidation reaction. So it is there to basically change the sign for you, which means when you go to an SRP table, you should not change the sign of anything you find in there, even though technically the reaction is written incorrectly and it should be an oxidation reaction. The negative is there for you to change the sign for you. If you do want to change the sign, which is perfectly fine, you would actually add the two values together rather than subtract. So at some point when we get there, you guys decide, do you want to add or do you want to subtract? Do you want to change the sign or not change the sign? And you should probably stick with one approach. Otherwise, if you change the sign and then make it negative, you just turn it back into sort of its original value. Probably everything I just said right now makes no sense to you, but it will eventually at some point when we get there. All right, just keep that in the back of your mind. But if we use this equation here, and in this case, our cathode is our hydrogen, which has a value of 0, and our cell voltage was 0.76. That gives us our anode value here, which in this case would then be our minus 0.76 volts, for our reduction of zinc, basically, right? So again, a reduction reaction that happens here. Now, if we hook the hydrogen electrode up here with our copper and do a similar sort of calculation using our standard hydrogen electrode as 0 and figuring out our voltage of the cell, which is 0.34 volts in this case. In this case, though, our standard hydrogen electrode is actually our anode in this case. And in this case, our copper is our cathode. This demonstrates an important part about galvanic cells. Pretty much anything can be an anode or cathode. It may or may not work, but you could use it for either side. And in this particular case, we do get, again, a reduction reaction here, basically copper adding a couple of electrons going to solid copper with a SRP value of 0.34. So this is a table of SRP values, and as you can maybe see, they're all written as reduction reactions and with their appropriate values there. Here's a better table that you could clearly not see. And this is also all reduction reactions that are written here. So you will typically need to go to an SRP table, and you have one obviously in your book as well. And you will see again that they are all reduction half reactions. So let's talk a little bit about the values that you'll find in these tables and what they mean. The E is for the reaction as it's written. So when you pull it out of this table, the E value that you are stating is really for the reduction half reaction that's happening. How do you know which one is going to be your anode or your cathode? When you are not given any information about how the reaction is happening, or you're not given an overall reaction that's going on, but you're just simply told, hey, I made a galvanic cell out of these two things. The way that you determine which one is your anode or cathode is by the more positive E value you find in the SRP table has a greater tendency to be reduced. So the anode or the cathode, which one gets reduced? Maybe if I move the fingers this way, do this, 50-50 shot. It's better than winning the lottery. 1.5 billion, I hear these days, or whatever it may be. Going to buy some tickets later. I don't know. Is it buying tickets now? All right, it is the cathode. Yes, that would be the one that gets reduced. Yes. So the cathode, gamble responsibly and only if you have the money to do so. All right. So cathode is the one that gets reduced. So in the absence of any information about how a reaction actually takes place, you can look on the SRP table, and the one that has the more positive SRP value should be your cathode, and the one that has obviously the less positive would then be your anode in that case. Half reactions are reversible. When you do reverse a reaction, what happens to the SRP value is the sign changes. So if it's negative, it becomes positive. If it's positive, it becomes negative. And changing the stoichiometry, which means in occasion when we talked about when you put the two half reactions together, you need to multiply the half reaction by a number to get the same number of electrons in each. You can multiply the half reaction by whatever number you need to do to get the balanced equation. It will have no effect on the actual SRP value that you have in there. So for example, one of the last ones, we multiplied the half reaction by 3. We would not multiply the SRP value by 3. We'd just leave it the way it is. So it'll have no effect on it. So let's go back to my wonderful talk about, this might make sense in a second. So let's say we took our classic one of, there it is right there. We'll go with, that's calcium, I think. Let's take, we'll take this guy here. We'll take this, which is the copper. And so the copper SRP value there, when you look it up in the table, and the reaction will look something like this. And was 0.34 volts. And I think, what do we have before that? We had zinc, I think, before that, I think, right? Yep. Zinc was minus 0.76, right? So zinc was minus 0.76 volts. All right, so this is like the classic example for redox reactions, the one everybody chooses. All right. So let's say we did a galvanic cell here. And by the way, if we were to build this galvanic cell, which one should be my cathode and which one should be my anode in this case? The more positive one is which one? It is the copper is more positive. It's not the negative value that I see there, right? So technically, based on the SRP value, this guy is more positive, which means the copper here should be my cathode. By default, this guy here would then be my anode, right? All right. Now we go to the equation I was talking about earlier, where everybody was looking at me under their breath of what is this guy talking about? Right? And we had basically E of the cell is equal to E of the cathode minus E of the anode in this case. When I want to go calculate E of the cell, I could either use this equation and just go to the table. And if all I need to do was just simply calculate the cell voltage, I could go into my E of my cell and go, my cathode value would be 0.34 volts minus my anode value, which is minus 0.76 volts. I'm going to grab my calculator because it's late in the day and give it the old college try of 0.34 plus 0.76 is 1.1 volts. Now, what is really happening in this case is you may also be asked to write the balanced equation. That means that my cathode reaction is correct the way it is written, right? 0.34 volts. But my anode reaction, this reaction right here, is it written as an anode? Is that an oxidation reaction? That is a reduction reaction, which means to make it the actual correct anode reaction, I would need to flip it around, which means my zinc solid would be over here going to my zinc with a +2 and my 2 electrons. Because I reversed the reaction, according to what we just saw, the sign of my value here now should become positive 0.76 volts, which means when I add this reaction together, my electrons cancel, gives me the overall reaction here that is going on. And now if I wanted the E of this cell, because I personally and professionally here changed the sign, which is actually the correct value for the way this reaction is written, I should not subtract it anymore. I should actually add those together because I changed the sign myself. And that would give me 0.34 volts plus 0.76 volts equals 1.1 volts. So because I changed the sign, I should not subtract it, because if I subtract it, I just put my sign back to where it originally was and I'll get the wrong answer. So that is what I was saying earlier. If you want to subtract to figure out the cell voltage, you should go to the table and just leave the sign alone, even though technically speaking, the one for the anode is the incorrect sign, because that's why the negative's there for you to change the sign for you. Now, if you want to do everything correct and you decide you want to change the sign, which you should do if you need to write the half reaction like we did on the bottom, then if you change the sign yourself, you should just add the values together. So decide whichever way you want to do that, and I would stick with it. Either don't change the sign and subtract, or change the anode side and add them together, but just don't do both. Change the sign and then subtract them. Yeah. Say it again. No, you need to always, because the SRP values, they pretty much are all standard reduction potentials. Every single reaction you see in that table is going to be the reduction one, which means every reaction you have in that table is perfect if you're dealing with the cathode. But when you're dealing with the anode, the reaction in that table is backwards. Yeah, so you got to flip them. So you always got to flip the sign for the anode, basically, if you want to add them together. That means you could have a value in there that's positive that you need to make negative, or you could have a value that's negative you need to make positive. So it wouldn't necessarily be the absolute value of that, because you could end up with a negative number for the anode part. So if you don't want to have to worry about flipping the sign and you're just trying to figure out the cell voltage, just leave the sign alone and subtract the cathode from the anode, and it will do it for you.